Welcome. This is a beginner first series on formal verification for digital hardware. If you are learning digital design, writing RTL, working in design verification, or coming from software and wondering how verification works, this series is for you. There are many commercial platforms out there such as Cadence Jasper, VC Formal, Siemens Questa, and many others, but you do not need any experience with those tools for this series. We will begin with the mental model so that you know what all we will cover. Across the series, we will move from the basic question of what formal verification actually means to writing properties, understanding constraints, debugging misleading results, handling proof complexity, and finally running a reproducible open source lab so that you can learn yourself. This part 0 is only the map, so I'm not going to compress 8 technical lessons into few minutes. When we describe hardware, we are not writing a list of instructions that runs one line at a time. We are defining logic that operates concurrently. Registers preserve state, multiple blocks react on the same clock, pipelines, caches, arbiters, interconnects, protocols, resets, power states, and security controls interact across many cycles. A block can look correct in isolation and still fail because 2 events arrive in an order we did not expect. A reset can release at the wrong moment. A request can be accepted twice. A response can be lost when 2 control paths overlap. And the internal state that caused the failure may be difficult to observe from outside the chip. That is why verification is not just reading the RTL and deciding that it looks reasonable. We need executable evidence that the implementation satisfies the design before it becomes silicon, where correction is slower and more expensive. So finally, in this series, we will focus on simulation and formal as 2 important functional verification approaches. They are not the only verification methods and they are not competitors. The useful question is what kind of evidence each method gives us. Okay, so to follow this series, you only need 3 foundations: basic Boolean logic, an understanding of clocks and registers, and the difference between combinational and sequential logic. It helps if you can read simple Verilog or SystemVerilog, but you do not need to know SystemVerilog Assertions or any formal tools syntax before we begin. So whenever we introduce any syntax, we will first state the requirement in plain English. Then we will connect that intent to the implementation and finally to the evidence produced by verification. So keep this relationship in mind: intent, implementation, and evidence. Part 1 asks the foundational question: what is formal verification and how is its answer different from what simulation tells us? We will begin with hardware verification itself and use a small controller to expose the difference between testing selected executions and checking a property across the model behavior. Part 2 goes beneath that result. We will turn RTL into a state transition system, separate possible states from reachable states, and build an intuition for how a proof engine reasons about the model. Part 3 is where an English requirement becomes a checker. We will introduce assertions, assumptions, covers, and the core SystemVerilog assertion ideas needed to express behavior across clock cycles. Part 4 focuses on constraints. A formal engine considers every behavior the model allows, so we need to describe the legal environment without accidentally excluding the bug we hope to find. Part 5 teaches us to distrust both red and green results until we understand them. A failure can come from the RTL, the property, or the environment itself. A pass can also mislead us when the property is weak or its trigger never occurs. Part 6 explains why formal verification times out. We will examine cone of influence, hierarchy, cut points, case splitting, helper properties, and abstraction as ways to reduce a difficult problem while preserving the behavior we care about. Part 7 asks when formal work is actually complete. We will connect requirements, property set completeness, reachable behavior, coverage, proof scope, regressions, waivers, and engineering review. Part 8 combines the workflow in an open source project. We will define a FIFO contract, add properties and covers, produce and inspect a counterexample, repair the RTL, rerun the task, and then transfer the same reasoning to a small fixed priority arbiter. You can think of the complete journey like this: understand the evidence, understand the model, write and review the verification intent, and then finally apply the workflow yourself. Watch part 1 and 2 in order because they stabilize the vocabulary and mental model throughout the series. Part 3 and part 4 belong together. One explains how we express what the design must do, and the other explains what environment behavior the proof is allowed to consider. The latter lesson focuses on debugging, complexity, coverage, sign-off, and the final hands-on workflow. Each lesson will have written notes, source link, original diagrams, and any example files that are useful for practice. And when code is involved, you can have the repository which will contain all the reviewed version used in the lesson. One final expectation before we begin. Formal verification is not magic, and a tool result is not a substitute for engineering judgment. So the model can be incomplete, the property can express the wrong requirement, the assumptions can hide behavior, and even the engine can stop without producing a complete proof. So throughout the series, we will learn how to read those limits instead of treating every green label as a truth. And if you want to follow the complete series, subscribe so you do not miss any next lesson. If you know someone learning RTL or verification, share this playlist with them and leave a like if this structure format is useful to you. We will begin with the most important distinction in the entire series, that is what simulation actually tells us versus what formal can stabilize, and how modern verification requires both. In part 1, I will show you the exact kind of execution that an apparently thorough simulation may still miss.